the second event in our interinstitutional program. Our guests are Professor Vermont from Montreal and Victor Rotger from Barcelona. They will be taking turns in giving a course on or around the Birch and Swinnerton-Dyer conjecture. And today's turn is Rotger's. The title is introduction, or just being the Birch and Swinnerton-Dyer conjecture.
Thank you very much, Vasily, for inviting the two of us to come here. So it's a pleasure to be here. It's my first time here in Moscow. It seems like a very nice place. And well, I mean, I will. My goal today is giving a background on elliptic curves, explaining the statement of this conjecture, the conjecture of Birch and Swinnerton-Dyer, explaining a little bit the state of the art, and also indicating some ideas in the proofs of some of the basic theorems regarding elliptic curves and so-called modularity of elliptic curves, relating elliptic curves to two modular forms. Okay, so, well, the basic object that we will be studying is our elliptic curves. So, an elliptic curve, as many of you, I guess, already know, I will use usually the letter E for elliptic curve over the field F is simply a smooth algebraic curve over F of genus 1 together with a choice of a point together with a choice of an F rational point that I will usually call O, because it will play the role of the origin. So this would be a choice of a point on the set of F rational points of this curve. Okay, not all genus 1 curves have a non-empty set of F rational points. So we are talking about genus 1 curves over a given field F, for which the set of F rational points is not empty, and in which case we just choose one and we call it O. Okay, and in very down-to-earth terms, if the characteristic of the field is different from 2 and 3, then this curve can be described by what people call a bias class equation, which is a form y squared equal to x cubed plus y 8x plus b. The fact that this curve is defined over F means that these A and B are numbers, elements in F, and the fact that it's smooth means that the discriminant of this cubic, namely this quantity, this is different from 0. This means that this curve is smooth. Okay, and here the point that is fixed as a distinguished point is chosen to be the only point at infinity in the projective closure of this affine equation. elliptic curves can be described by such simple equations. And then if for instance, you take f to be the field of real numbers, and if you plot this equation, you either have something like this, or something like this. This is the typical shape of the real locus of an elliptic curve. And if you have 2 points, say P and Q, on this elliptic curve, there is a natural addition law on the set of points, which is that if you take the line joining them, and then you take this vertical line, you define this to be P plus Q, and this gives a structure of an abelian group on the set of rational points on the elliptic curve. This can be done for any field, and geometrically on the real locus, it takes this picture. So in general, this set it's not only a set, but it has natural structure of an abelian group. And this striking fact, which is very classical, presents most of the mysteries of the arithmetic of elliptic curves. When the field is the field of real numbers or field of complex numbers, the structure of this group is quite well understood. For instance, if we have that the ground field F is the complex numbers, then this is not a very mysterious group. This is just a lattice. So if F is the field of complex numbers, then the set of points of complex points, this is topologically, this is just torus. And as an abelian group, this is isomorphic to the complex numbers, the complex plane, quotient by a lattice, where tau can be taken to be a complex number whose imaginary part is positive. And therefore, this is a very rather simple abelian group, so there are no so many mysteries about that. But notice that from this it already follows, from this description, it follows that the subgroup for a given n, for given a positive integer n, if we look at the n torsion, and I will write it like this, this is by definition the subgroup of points such that np is the identity element, the origin, the fixed point that I chose at the beginning. This is isomorphic as an abelian group to 2 copies of Z mod nz. Okay, and as a consequence, this is also true for any field of characteristic 0 when we take its algebraic closure. Okay, which are other fields that have an arithmetic interest? So the next fields that we could consider could be, if instead of taking the real numbers or the complex numbers, we can also consider elliptic curves over finite fields. So if I now take a finite field, so if F is, for instance, the field of P elements, where P is a prime number, or more generally, F is a finite field of Q elements, where Q is some power of a prime, then it's clear that the set of points on the elliptic curve with coordinates of these finite fields is, since the only possibilities for x and y range among the elements in the finite field, this is an abelian group which is finite, and its cardinality can be bounded, and there is a famous theorem due to Weil, it is known as Weil's bound, which asserts that the cardinality, the number of elements, the number of rational points here is q plus 1 minus an integer which I will call aq or p, where this number is an integer satisfies. Okay, so let me put here inequality, that its absolute value is less than or equal to the square root of 2. So this is known as Weil's bound. Okay, so this is one of the most important theorems we know about the size of the set of rational points of an elliptic curve over a finite field. Okay, let's consider now another class of fields, which is also very natural and classical. And although they are very classical fields, we know very little about the set of rational points over these fields, which is the case when we consider F to be simply the field of rational numbers. Or, since most of the statements that I will claim about this field are also valid in more generality, or more generally, when F is what people call a number field. This is just a name for a finite extension of Q, like for example, a quadratic extension, where it is an integer, or a cyclotomic field, which is the field that you obtain when you adjoin a root of unity. Okay. So all the statements I will make about the set of rational points over F are valid for the field of rational numbers or for any finite extension of F, which is what we call a number field. And here we know very little. We know some things, but as most of you already know, the conjecture of Birch and Swinnerton-Dyer really has to do with the structure as an abelian group of the set of rational points of the elliptic curve over Q or over a number field. So let me explain what we know already, and also what we don't know, and the kind of questions that we would like to answer. So the most fundamental theorem is known as the Mordell-Weil theorem. And since some of the ingredients in the proof of this theorem will be important later in the subsequent lectures, if I have time at the end of this talk, I will explain some of the ideas in the proof. But for now, let me just state the theorem as it is. So it says that if F is a number field, think simply of Q, if you wish, then the abelian group of f rational points, the set of solutions to the Weierstrass equation, is a finally generated abelian group. Is finally generated. So, in practice, if we have an abelian group, which we know that it's finally generated, we have a structure theorem of this kind of abelian groups. And this is equivalent to saying that as an abelian group, there is an isomorphism of abstract groups where Z is the group of integers, R is some non-negative integer, is called the rank of the elliptic curve, okay. When I write the rank of E, I really mean the rank of E over F. I mean, if I really want to emphasize this, I will insist in remembering that I'm considering this curve over F, because notice that if I have an extension of F, say K, an extension of F, and if E is an elliptic curve defined over F, I can also regard it as a curve defined over a larger field. And the rank of the elliptic curve over larger fields in general will grow and will change. Okay? So this is this R, and T is what we call the torsion of D. And these are just the points on the Mordor group, on the group of rational points. Okay. And notice here the difference. If we consider the set of rational points over the complex numbers, the torsion of this group, those points which are killed by some large enough integer, this is an infinite subgroup, because for every n, there are n torsion points. I told you before that for every fixed n, the n torsion part is isomorphic to 2 copies of z mod n. So there are infinitely many torsion points. If I look now at the Q rational points of an elliptic curve over Q or a number field, then this theorem is claiming that there are only finitely many torsion points. Or in other words, for n large enough, the n torsion is trivial. Okay, so this means that in order to understand this group, there are 2 invariants that we need to be able to compute. If we are able to compute this finite group T, and we are able to compute this rank, we are done. This means that we understand perfectly well the structure of this group. Okay? So among these 2 invariants, R and T is less mysterious than R. So we know of methods that allow us to compute in practice T, and also we have important theorems describing this subgroup T. T is not very mysterious. We know of techniques that allow us to compute it in practice, in examples. Mainly due to Roots and Nagel and other methods to compute distortion part in practice. And if you want a more general conceptual statement, there is a famous theorem of Mazur Barry-Mazur's theorem. That if we take, for instance, F to be the field of rational numbers, then the torsion of the elliptic curve, or Q, has only finally many different possibilities. Namely, it's either isomorphic to Z mod n for n equal to 1 up to 10 or 12, or it can be isomorphic to 2 copies of Z mod 2 Z mod 2 times Z mod 4 These are all the possible possibilities. This means that there are only 16 cases, and therefore the largest possible torsion has cardinality 16. So this means that we have a very good control of which are the possible torsions of groups of an elliptic curve over Q. And there are also theorems which generalize this theorem of Mazur to arbitrary number fields due to Merel and Pierre-Parent. This is an area which is quite well controlled, although of course there are still many open questions. But we can say that we have a good knowledge of what happens.
Why 16? It's even 50.
Sorry? 2 times 8, 16?
No, you have said that 16 cases. But
No. 16, so 10, okay, so 15. Sorry.
It's true that for larger number of fields, we still get a finite list of them.
Yes. Yes. Any more questions about this? Feel free to ask any question or any level. I know that some of you know all this much better than me, and some of you perhaps you are just beginners, so just ask anything you wish.
If you look for elliptic curve or a field of rational functions, the answer is the same.
I don't know. I don't know. I mean, I would expect. What do you think of that? If it's the field of fraction over a finite field, then yes. If it's a global field, then yes. If it's a field of fraction, say Q of t, then I guess so the same. But I mean, there are many theorems. I mean, you can look for that. More questions?
But can you always give a complete list for any extension of Q?
No, this is a more difficult question. I mean, if you look for a completely general statement that for any number field F, which are the possible structures, this is a much harder problem because this number field F can be very large. But you can prove that there are always most limited number of possibilities. And in some cases, for instance, when F is a quadratic field, you can have some classification theorems. But as you see, there are many open questions here.
And can you, so does this 12 have some meaning for you? And
Yes, if you look at the proof of Mazur's theorem, this has to do with what people call the modular interpretation in terms of modular curves. I will explain later what a modular curve is, but this is very related to the question of whether some modular curves have rational points or not. And these curves, the modular curves which are behind these ones, are typically modular curves of genus 0 or genus 1, which are curves which tend to have many rational points. But as soon as the genus of these modular curves is large, you don't expect them to have rational points, which implies that there are no curves with given torsion. Okay, but these concepts of modular curves and the modular interpretations, I will explain them a little bit more in detail later. Okay, so that's a very good question. Okay, so I hope I sort of convinced you that the torsion is something more or less controlled, although if you like this area, you will find many questions to research about. And on the other side, the other invariant, the rank, which is just a number, a non-negative number, it's much more mysterious. So the rank is much more mysterious. Note as a trivial observation that knowing the rank, so the set of points is infinite if and only if the rank is positive. Okay, because when the rank is positive, this means that there is this one copy of set, and therefore there are infinitely many points here. And if the rank is 0, this means that the only rational points over this number field are the torsion ones, which I said it's a finite group. So this means that for elliptic curves over a number field, you can have this dichotomy. You can find elliptic curves with finitely many rational points, and you can find elliptic curves with infinitely many rational points. This is a trivial observation given the theorem of Morton-Weil, but perhaps this is good to compare with another theorem. Perhaps it's the right moment to state now. It's a theorem of Halting's, Gerard Halting's, which was, before it was proved, known as the Mordell conjecture, so the conjecture of Mordell, the same Mordell as in the Mordell theorem, which says that if X is an algebraic curve, a smooth algebraic curve of genus at least 2, the genus topologically is, if you look at the Riemann surface, the genus is the number of poles in this compact Riemann surface. So if the genus is at least 2, and this is a curve over a number field, then the set of rational points, the set of pairs of coordinates x, y, which are solutions of the equation attached to this curve, and which are both x and y lying in F. This is a set which has no natural structure of group, but as a set, this is always a finite set. There is always finitely many F rational points on the genus G greater than 2 curve. Okay, and so elliptic curves are very special in that it's in genus 1 where it is possible that a curve can have infinitely many points. When the genus is 0 or 1, curve can have infinitely many points. But the case of genus 0 is not special, no, it's not very difficult to understand, because if a genus 0 curve has at least 1 point, then it has infinitely many. So there is not much mystery. But curves of genus 1 present this mystery that they can have both finitely many or infinitely many. As for this setting, when the curve has genus at least 2, perhaps it's interesting to mention the following theorem of Bhargava, the recent field medalist. This is a theorem, the last of 2013, which is the following. As the genus G goes to infinity, and we consider not all possible curves of genus G, but only those which are called hyperelliptic. So the same as the following. A density of 100%, so all of hyperelliptic curves of genus G So a hyperelliptic curve is a curve. Hyperelliptic means the following. A curve is called hyperelliptic if it can be described by the following simple equation. So y squared equal to any polynomial in x of any degree. The relation between the degree n and the genus g is very simple. There is a linear relation. It's roughly the genus g is n minus 1 times a minus 2 divided by 2, something like this. So when g grows, the degree also grows. Okay, and the theorem says the following. A density of 100% of hyperelliptic curves of given genus has no rational points at all. With this I mean, if you look at the set of hyperelliptic curves of genus 2, Bhargava computed which is the density of those curves which have no rational points. He computed this density, and it's, I don't remember, say 73%. When the genus is 3, he also computed the density, and he computed it to be 75%. And as the genus grows, this density tends to 100%. So in words, in simple words, when you look at these equations, if n is 3, this is an elliptic curve, and this will be the source of all our problems. But when n grows, it's very difficult for them to have rational points over a number. Okay? So, if the genus is 1, so for elliptic curves,
Excuse me.
yes?
What do you mean by density? If you fix the genus?
You fix the genus. You say genus 2.
You have to find the remaining.
You have found the remaining, so now you have to index this set of curves in some way. Okay? For instance, right? Say for instance that you take n equal to 5.
Okay.
Okay? This means that the genus is 2. Okay? And now you order this set of curves by the growth of these coefficients. Okay? So if you say, which are those hyperelliptic curves of growth of height, people say height, at most 10. This means that the absolute value of all these coefficients are at most 10. Okay? Here you have finitely many such curves up to isomorphism. Okay? And then among them, you count which have rational points and which not. This is a proportion. When you let that this height grow, these coefficients grow, you can take the limit. And this is what you call the density. Okay? It's clear? It's a very concrete statement. This is for G. Then you do the same computation for larger and larger C. This density, Bhargava proves that it's tending to 100%. Okay, so let's see what happens, or what do we expect to happen for elliptic curves. If I have an elliptic curve over a number field F, the conjecture is that, and now with the same meaning, 50% of them. So now an elliptic curve is such an equation with n equal to 3. I order them by height, by the size of the coefficients. Okay, and the conjecture is that 50% of them, half of them, should have rank 0. This is a conjecture. Okay, and the other 50% should have rank 1. This is a conjecture. This is a folkloric conjecture. I don't know if this conjecture is attributed to anybody in particular, but this is the general expectation. I don't know whether this is disappointing for you or not, because everything would be much more problematic, perhaps, if there were elliptic curves of any rank, but there are elliptic curves of high rank. It is also proof that, don't be confused, because we also know that there are infinitely many elliptic curves of rank R greater or equal than 6. So when I say that 50% we expect that they have rank 0, and 50% we expect that they should have rank 1, first of all, we don't know whether this is true or not. This is a conjecture. But believing this conjecture, this leaves room for infinitely many other elliptic curves of density 0, as I said, imagine the space of elliptic curves as a parameter space. This is a continuum. And in this space, there are infinitely many points placed in a discrete way, so that if you measure them, the volume is 0, but there are infinitely many of them, for which the rank is at least 2. This is a theorem. It is proved that there are infinitely many elliptic curves having rank at least 2. But at the same time, you expect that they are very sparse. There are very few of them compared to the immensity of elliptic curves having rank 0 or 1. And the truth is that if you give me a random elliptic curve and you are able to compute the rank, most of the chances is that this will have either rank 0 or rank 1. If you go to tables and you try to look for elliptic curves having rank 2 or more, well, you will find them, but they are not so abundant. Okay? Okay. Bhargava proved the following result towards this conjecture. He proved this together with his student Arul Shankar, which is the following. At least 20% of elliptic curves over Q have rank 0. Okay, the expectation is that 50% of them should have rank 0 and no more. He proved that at least 30% of them. And he also proved that at least 80% of them, of elliptic curves over Q, have rank 0 or 1. We expect 100% of them to have 0 or 1 because we expect 50% having rank 0 and 50% having rank 1. So this should be 100 and this should be 50. Bhargava and Shankar were able to prove these lower ones. Okay? Any questions?
Yeah, I have a question. Would you consider the set of all quadratic twists of a given curve?
Yes.
What do we know? Just the old Wells-Bourget's result, or anything about
So,
as well?
again, the expectation would say is that we should have 50%, 50%, like that. And I don't know state of the art. I don't know how much is proved or not. Do you know better?
No.
Do you know? There are many results in this direction, so we can make a search and see which is the latest result. But there are more results in this direction. This is a much deeper result because it's not considered only the twists, but all the fauna of the liquid. Okay, so this is one kind of results, but of course, we would like to know for a given elliptic curve, having a more conceptual understanding of what the rank should be, because the rank can be very large. There are examples of elliptic curves of rank 20 or 30, and we don't know whether there are elliptic curves of arbitrarily large rank over Q. This is also something that we don't know. We don't know if there are elliptic curves over Q having rank 1000. Some people believe that there is an upper bound. Some other people believe that there should be elliptic curves over Q having larger and larger rank. This is completely open. And let me now explain the conjecture of Birch and Swinnerton-Dyer, which offers a conceptual description in terms of analytic functions of the rank. Okay, so everything I will explain now will be valid for any number field, but since there is no more complication or there is no essential simplification, if we assume that F is a field of rational numbers, I will just assume that just for notational simplification. But it's not that I will be explaining things that are true for the rational numbers and which are false for number fields. Everything I will explain for F equal to Q. But this is only for notational simplicity. Everything I will say has a very natural and easy analog for finite extensions of Q. Okay? Okay, so associated to E, to an elliptic curve over Q, there is what people call the L series or the L function of the elliptic curve. Okay, so that means I will do it for any number field, because I just remember that there are some things which are not true for large number fields, and it's interesting for you to know. So assume F is a number field. So E will be an elliptic curve over number field. And if you wish, for you can keep F equal to Q as a basic example. So there is the L function of the elliptic curve over this field. And this will be an analytic, a holomorphic function defined on an open subset of the complex numbers. Those whose real part is larger than 3/2, with complex values. Okay, defined as follows. It will be defined by means of an infinite product that it will converge precisely for complex values of S, satisfied that the real part is at least 3/2, and it's the following. For every prime P, so for every prime ideal P of F, so if F is the field of rational numbers, I just mean for every usual prime number, okay? And if you know what's the prime ideal in a number field, so it's just the same. Otherwise, just stay with the rational numbers. For every prime ideal P of F, define the norm of P to be F is my number field. Let me call Z of F what people call the ring of integers of F. So if F is the rational numbers, these are the classical integers. And you can quotient, you can mod out by this ideal. So in the classical setting of the rational numbers, this is just Z mod P. Okay? And this is in general a finite field. And we can take its cardinality, which is a prime number or a power of a prime number. Okay. Okay, and this quotient is called the residue field of P. Okay, and define also a polynomial attached to this prime P in some variable, call it x, for instance. This will be a polynomial, the following polynomial: 1 minus AP of P x plus the norm of P x squared for every prime not dividing the discriminant of the elliptic curve. Remember that the discriminant of the elliptic curve was roughly 4a cubed plus 27b squared. So this was a number, an element in F. So we are asking these prime ideals or these prime numbers not to divide this element, this quantity. And here, this AP of E is a quantity that already appeared before when we were considering elliptic curves or finite fields. Where? Remember that we have our elliptic curve over F. It's given by a Weierstrass equation defined by coefficients A and B. I can look at these coefficients mod P, and therefore I can consider this elliptic curve modulo P. This is now an elliptic curve over the finite field, and the cardinality is given by the cardinality of this field plus 1 minus a P of it. Well, remember that this number a is an integer satisfying Bell's bond. Okay, this is a number attached to the elliptic curve and this prime ideal P that already appeared before. Okay, so with these two definitions, I am already in position of defining this L series, which is as follows.
Square root of F.
Ah, yes. Thank you. So, given any of these polynomials, this was a degree 2 polynomial, make the following change of variable, replace x by the norm of P raised to minus s, invert this, and take the product of over all prime ideals. Okay? Here I only defined these polynomials for primes not dividing the discriminant. I left out only finitely many prime ideals. So if you wish, it doesn't matter so much. If you prefer not to include those finitely many ideals dividing the discriminant, it's fine. And in fact, one can define polynomials also for primes dividing the discriminant in a similar way. For simplicity, I'm going to stay here on the platform. Okay? So this is the definition of the L series. And it is precisely this bound, square root, that is exploited in order to prove that this infinite product, as P ranges over all primes, is convergent when S is a complex number satisfying that its real part is larger than 3 parts. And also, the convergence is absolutely uniformly convergent in locally compact subsets. And therefore, this implies that this is not only convergent pointwise, but it also leads to a holomorphic analytic function on this open subset. Okay.
And this product also convert if we take a curve of higher genus.
Yes.
Has this.
Yes. If you have a curve of hypergenus, you have to modify this definition of this polynomial. It will be a polynomial of degree 2g, where g is a genus. Okay. And then you can also define what people call the real function of the curve.
Okay.
Sometimes this is also called the zeta function of the curve. Okay. There are these two names, zeta function, L function. They are very often synonymous. Okay. Depending on the literature, people use L function or zeta function. Okay, this is the analog of the classical Riemann zeta function. Okay, the Riemann zeta function is defined exactly in the same spirit, where this polynomial for the Riemann zeta function has degree 1. Okay. It's simply 1 minus p times x. So, okay. So this is a very standard machine for constructing zeta functions, and this is not just an ad hoc definition. This is just part of a definition that applies to many arithmetic objects. Okay. Okay. So this is a holomorphic function. This induces a holomorphic function. Okay. V is this open subset of the complex numbers. But the conjecture let's call it the modularity conjecture. Is that this holomorphic function on this open subset V should actually extend to a holomorphic function on the whole complex plane. Okay, extends to an analytic holomorphic function on the whole complex plane. And also, people expect, and I will tell you now in which cases this has been already proved, because it has been proved in many cases by Andrew Wiles and his school, but in general it is not known, that this function, it satisfies a functional equation relating this function to this one. Okay, there is a very precise recipe for the functional equation, but since a priori you should be able to extend this function to the whole complex numbers, part B makes sense, and says that the values at the point S, so a priori this is only defined on the right of this line, but we predict that it should be extended to the whole complex plane, and the values at S and 2 minus S should be related once you extend it analytically to the whole complex plane. Okay. So later I will explain, if I have time, I don't know how much time I have, some of the ideas behind the proof of this theorem. And let me now explain in which cases we know that, and so more or less what do we know about this conjecture, because it's very, very important for the very statement of the conjecture of Birch and Swinnerton-Dyer. You have already some knowledge of this conjecture of Birch and Swinnerton-Dyer. You perhaps already know that it has to do with the value of this L function, of this holomorphic function, at S equal to 1. Hence, this conjecture doesn't make sense if we don't believe in part A. Okay? Also note that S equal to 1 is exactly the point of symmetry of this functional equation. Okay? When S is equal to 2 minus S, this happens when S is equal to 1. So this functional equation makes S equal to 1 a particularly interesting. Okay? This is also has a natural analog for the classical Riemann zeta function, where the functional equation of the classical Riemann zeta function relates S to 1 minus S, and therefore the line where the real part is 1/2 has a special relevance, and the Riemann hypothesis is concerned with this line. So something similar happens here. The point of symmetry in this functional equation is particularly interesting. Okay, so let me explain what do we know about this conjecture.
Isn't B a theorem?
Yeah?
Isn't B a theorem? I mean,
This is not a theorem yet. Is this a question? This is okay. It's normal that you're confused perhaps because this is a theorem when the number field F is Q. Okay, this is what I'm going to say now. So, and this is the famous theorem of Andrew Martins. Okay? Okay, there are many mathematicians who have contributed to this conjecture. Okay, and it's very difficult to say which is the state of the art because every day there is a new contribution, and every day people know a little bit more about this conjecture. So I will explain more or less what is the state of the art up to yesterday, so to say. So the first, let me call it the modularity theorem. Okay, because later you will see that modular forms and modular curves that I didn't introduce yet play an important role in the proof of this theorem. But for now, let me just state the theorem. So the conjecture, both A and B, okay, so this is what you have in mind, I think. This is true for all elliptic curves of Q, and for almost all. And when I say almost all, I'm not going to specify the details. It's for almost all elliptic curves satisfying some technical condition, which is satisfied for almost all elliptic curves, but perhaps some of them. E over F, where F is what people call a totally real field. And since this is important, let me recall what is a totally real field. A totally real field is a field that is a field such that all embeddings from the number field F to the complex numbers factor through the field of real numbers. This is the definition of a totally real number field. All embeddings of, for instance, if I take Q of the square root of B, if this is a positive number, this is a totally real field. If B is negative, this is not totally real. Cyclotomic field, which is a field in which you adjoin to Q a root of unity, this is never a totally real field unless the root of unity that you took was 1 or minus 1. Okay? So this is a class of number fields, which is very important because for this class of number fields, people are able to say much more than for a general number field. And the reason is that there is a natural analog of modular forms for totally real number fields, which are called Hilbert modular forms. Okay? And the geometric objects that arise in the proof of this theorem are well understood. While for general number fields, the geometry and the type of modular forms that arise in the proof are much less understood. Okay, so this is something we know, and also, okay, so let me just put this part so that I don't, I have more time to explain other things. Okay. Okay, so this is a theorem of Wiles and many other people. Diamond, Skinner, Braille, many people. So this means that at least for this class of elliptic curves, for all elliptic curves over Q and say for almost all elliptic curves over totally real fields, this is true, and therefore it makes sense to talk about the value of this holomorphic function at s equal to 1. And in general, since we believe this conjecture, I will assume from now on that f is an arbitrary number field for which we know that this conjecture is true. Okay, so that we can speak about that. So assume for the rest of these lectures okay. So if we want to assume that the ground field is rational numbers, okay, the conjecture, I can now state the conjecture of Birch and Swinnerton-Dyer. Any questions so far?
Do we go for a 5-minute break?
Sure. Now is the
For some ventilation.
okay. So whoever stays will. Of elliptic curve is equal, this conjecture should be equal to considering the L series and assuming perhaps because people already proved that this is a function of the whole complex plane, so that it makes sense to consider its value at s equal to 1. This function at s equal to 1 may vanish, may be 0 or not, and if it's 0, that its derivative might be 0 or not, and if its derivative is 0, its second derivative may be 0 or not. So we can talk about the order of vanishing, so how many non-zero derivatives at s equal to 1 there are. So these two numbers, invariants, should be equal. And, well, if you think about that, this is a very striking conjecture, because this number, the rank, this is the number of linearly independent points in the group of f rational points of the curve. F, say, for instance, is the field of rational numbers. So, if E is divided over Q, this is the R is the number of linearly independent points in the group of Q rational points of the elliptic curve. This is what people refer to as a global invariant. While this function is constructed by a much simpler construction which only takes into account the number of rational points on the elliptic curve modulo all the primes. So this has into account only the behavior of the elliptic curve modulo all possible primes. The number of rational points on E modulo 2, 3, 5, 7. This is what people call local information. The information that you get from an object looking at its behavior at primes is called the local behavior of this object. And we are here packaging together all this local data. And from all this local data, if the conjecture were true, we should be able to understand what is the rank, which we consider to be a much more mysterious invariant, and what we call a global invariant, because it has to do with the behavior of this elliptic curve over Q, which is what people call a global field. Okay. So let me explain a little bit the intuition that perhaps Birch and Swinnerton-Dyer had in order to suspect that this was true. Of course, they checked this numerically for many elliptic curves, for what people know as CM elliptic curves. So they could check this numerically for many curves. But besides checking this numerically for some curves, they also had probably the following insight. And it's the following. Let me explain you this insight when F is Q. So that, let me now remember what is the definition of this function when the ground field is Q. So that these are now just prime numbers. And this polynomial, there was an inverse here, so let me put it like this way. The polynomial which had degree 2 was, let me just assume for simplicity here that these primes are not divided in discriminant, so the definition that I gave was the correct one. And this was 1 minus AP of P x, and I will have to replace this x by P to the minus s, but I will do this later, plus the norm of P, which is simply P x squared. And now, the recipe said that we had to replace this x by P to the minus x. So this is times P, and this is times P to the minus 2s. This is the definition, which notice that it's very similar to the definition of the Riemann-Zeta function. It's just that the Riemann-Zeta function is this one, this guy equal to 1, and here instead is slightly more complicated because we have a degree 2 polynomial. So now, if you evaluate this infinite product at s equal to 1, this does not converge, because I already told you before that this infinite product only converges for those complex numbers s whose real part is at least 3 halves. But if you still insist and say, okay, let me see what does it look like if I just plug in s equal to 1 in this infinite product. So if you just plug it, s is equal to 1, and you can do the same for any number field. I'm just doing it for Q just for simplicity, but if you do the same exercise, okay, so this is infinity. This is not a number. But if you look at the shape of this product, this is, well, let me just substitute s equal to 1 here.